The thing is, I've also forgotten a bit since it's been a while how the proof went, but we'll see. Okay, so last time, yeah, maybe it's worth drawing the chalk. Okay, so so let's start with the recall, which is, so definition 3.6 says.
Sorry, on Saturday you will take class because I think it's scheduled for you.
Oh really?
Yeah.
Okay. Yeah, then I will. Yeah, I mean, if there's a class scheduled, I'll do it. But yeah, thank you for telling me. Otherwise, I would not be prepared. Okay, good. Okay, so definition 3.6, you already have it written, right? So we can quickly recall it. So I'll not write the full thing very clearly. So this is just a recall informal. So we had a challenger, right? And the challenger was sampling 5051 from this spherical measure such that 5051 are orthogonal, right? And it would sample B from 0, 1, and then it would define phi sub B, divide it into two registers, right? Like two paths, basically. And then one part, so let's call it RA, RB, because these are the registers, sends RA to, RB, RC. So RB and RC sends RB and a description of 5051, right? To B, that makes this 5051 measurement and gets outcome B sub B, and then sends RC and then description of 5051. So the same thing, except you're sending register C, also make some 5051 measurements. But these measurements can be different, right? They don't have to be the same. And then the output B sub B, and you win when B equals BB equals BC, right? So this was the game, right, that we were looking at. Okay, and we had defined an expression. Okay, so let's recall. Then we had defined. So recall that we had defined G of 5051, right? As the maximization, so it was like basically maximize pi b's and pi c's, and then this is the probability that you win in this game. Okay, so this is probability. Can write BC win. I can write here BC win. Okay, good. So this is where we were. And last time we managed to show the following. So we showed that. Okay, and this is also the probability that given pi b, pi c. Okay, which is also the probability that BC win. Okay, and last time we showed the following. So we showed that BC wins. So this was one of the nodes. So BC win, given that they used 5051, right? So this 5051, some specific choice was used. This we showed was half the trace distance between rho 0b, rho 1b, plus trace distance rho 0c, rho 1c. Okay, where these are, so you trace out C from phi sub B, phi sub B. Here you trace out B, phi sub B. Right? That was the. It's making sense, right? Like we already covered. Oh. Okay, good. And okay, so we're now going to continue from there. So we want to get, so we take expectation over phi 0 and phi 1 to get probability that BC win, right? And this is going to be the following. So probability that BC win is going to be expectation over phi 0, phi 1 sampled from UN. Phi 0, phi 1 inner product is 0. Probability BC win given phi 0, phi 1, right? So far I've done nothing, it's just conditional probabilities. Okay, so now we can make the substitution. Using the first NB, phi 0, phi 1, mu n, phi 0, phi 1. Okay. And I suppose that you get this inequality, right? Because you will have, you're optimizing the measurement, assuming you have the description. That should actually work. I suppose this could also be equality. I don't see why this has to be an inequality, unless I missed something. But okay, the next one has to be an inequality. So the next one is, so we'll prove this. Okay, so this star step we'll prove in just a second. But one can remove the requirement that the vectors are orthogonal. Okay, and so one can write just the following. So phi 0, phi 1, sample from mu n, half trace distance, rho 0 b, rho 1 b, plus trace distance, rho 0 c, rho 1 c, minus a negligible function. So removing this orthogonality condition gives you a penalty of a negligible function, which we'll prove in just a second. And then we know that, so we computed in theorem 3.5 that this quantity is going to be a quarter and 1 by pi minus epsilon. Okay, so this is using theorem 3.5. Okay, and this will be greater than 0.568 for lambda tending to infinity. What is epsilon? It's probably the negligible function. I'm guessing it's another negligible function. So theorem 3.5 I think was just saying that if you sample, do you remember the theorem? 3.5. Yeah, so 3.5 was basically just saying that, effectively that trace distance. So this is recall theorem 3.5. So we're saying that the trace distance between rho 1 and rho 2 with a high probability, so almost surely goes to 1 by 4 plus 1 by pi, which is approximately 0.568 when psi 1 and psi 2 are sampled basically from the spherical measure. Okay, and rho 1, rho 2 are the reduced states, 1/2. Okay, so that's roughly the informal recall. Okay, so we got it to this point. We just had to remove this fact that they're orthogonal, right, to be able to use the theorem.
Why do you have like there also greater than equal to 0?
I suppose they probably didn't do it very carefully, because this is like almost surely, so maybe there are some like there's some asymptotic statement that needs to be
Yeah, almost surely. I mean, there could be plus or minus both that goes to 0.
yeah, so that's why you take the minus and put an inequality. You need a lower bound.
So that epsilon must be related to this.
Negligible, yeah. But I don't think the paper does it explicitly. Because the theorem itself is a bit like it just says almost surely, doesn't give you like the exact thing. So I guess it's probably okay. I mean, but yeah, I didn't actually work out all the details.
The probabilistic statement is.
Yeah. Okay, good. So now it remains to show the star step, right? But okay, so the bottom line is assuming star works, right? So assuming star. We've proved that. So we've proved basically theorem 3.2, right, which was saying that is every deterministic scheme can be attacked. Okay, because this game was basically equivalent to the attack strategy that we had given for the initial unclonable encryption game with the deterministic scheme, right? Okay, so you can go back and check. So these 5051 were like related to this, that you have zeros and you're applying some UK, and then there were 001, right? And you were applying UK. And the strategy was that you apply some hard random unitary, then you give the description of these two things and the state. So that's essentially what 5051 were in the construction, right? And then we argued that this description is equivalent to the attack, and so we just analyze the success probability of this, and we get a lower bound which is strictly greater than half, right? Which violates the security of the scheme, which said that it should be at most half plus negligible. Okay, so it remains to do the star step. So let's do that. Okay, so now we do the star step. So here's star. So NB. Now we're really in the weeds. Okay, but let's do it. So for an arbitrary phi1, okay, given phi0, one can write phi1 as alpha phi0 plus square root 1 minus alpha mod square phi0 perp. Right, that's just by Schmidt decomposition, where alpha is just phi0 phi1 and phi0 perp is obviously perpendicular to phi0, right? And you can absorb the phase into phi0 perp, whatever it might be. Okay. Oh. Very well. Okay. So by symmetry, we have that expectation over phi1 from the spherical measure mod alpha square has to be 1 by 2 to the lambda. Okay, so what it's saying is that if you fix any direction. Okay, so that's phi 0, right? So phi 0 is some, say, arbitrary vector which you fixed. Now if you pick a random vector, the probability that you would have so on an average, the component along this arbitrary vector is going to be 1 by 2 to the lambda, and that basically you can just check by normalization. Okay, I'll leave it as an exercise. It's not too hard because all the components have to essentially sum to 1, right? And by symmetry, all components are equivalent, right? So each component has to have 1 by 2 to the lambda to get the normalization.
What is lambda?
Lambda would be the number of registers, I guess. So these vectors are on lambda many qubits. Okay, so this is fine. Okay. Okay, so now did I mess up the pages? Okay. So now we take epsilon equals lambda to the minus lambda by 2, kappa equals 2, and f of psi equals psi phi 0 mod square in lemma 3.4. What was lemma 3.4?
But this answer assumes that step phi 1 is full. No, I think that's your mistake.
Yeah. These are
Phi 1 should be full rank step. Get phi 1, bra phi 1 should be full rank step to get this. I mean, this
rank. Where are you getting ranks? These are not density matrices, right?
Yeah, if
It'll be
I
rank
do the
1.
Integral, then I will have integral over phi 1, get phi 1, bra phi 1. I replace value of alpha, right? So you write expectation over phi 1, and I write the alpha value there.
Expectation over phi 1, I write there. Yeah.
I will replace mod alpha square by bra phi 0, get phi 1, bra phi 1, get phi 0, right? So you have a matrix get phi 1, bra phi 1 whose expectation value you are computing.
Yeah.
And that will be given by the trace of that operator times identity by the dimension. Oh yeah, it doesn't matter because trace is always.
Okay. Yeah, I mean the argument I was giving was very straightforward. It was just saying that you fix, like, so phi 0 is fixed for you, and you can complete the basis in whichever way you want. Okay, and say this component is alpha 0, this is alpha 1, alpha 2, and so on. So you'll have alpha to the lambda, right? Well, let's just start with okay, whatever. Okay, so you'll have all these components, and the point is that because the vector is chosen uniformly at random, the expectation of each of the alphas is identical, right, by symmetry, and they have to sum to 1. So the expectation. So that's all I was saying. Wasn't saying anything very deep.
Yeah, if you read Nielsen, then this is also one line proof for like just doing the integral without arguing anything.
Okay. Yeah, I'll ask you later. You can tell me. Okay, and now we need the lemma. So lemma 3.4, which was it was one of the technical statements, right? Which is it's Levy's lemma. Okay, so Levy's lemma, recall, was saying what? So it was saying that if you have some functions, okay, so informal, so recall. So informally, what the statement was as follows. It was saying that if you know that so f is a function, right, that goes from the vector space to a real number. Sorry, takes a vector to a real number. Okay. And you know that this real number, the difference is at most kappa times phi minus psi, the norm, 2 norm, okay, for some chi, for some k, or some kappa. Then there exists a constant delta such that for all epsilon greater than 0, probability that you sample psi from the spherical measure, that your f of psi minus the expectation of the same object, so f of phi okay, that this so it deviates from the average value by a factor greater than epsilon, with probability at most exponentially small, right? So this was the explicit bound delta epsilon to the n by kappa square. Okay. So now they're arguing that if you take epsilon, also I think the mu here is probably, yeah, no, it is n. Yeah, I don't know why there's n and lambda actually. It should probably be the same. I don't know if I'm missing something. But okay. So you know, the function f that we take is the component of psi along phi 0. Okay. And so the kappa is, they take kappa to be 2. Okay. Yeah. Because this is the one norm, that's the 2 norm, so it will not exceed 2 values. I'm kind of assuming that I didn't actually prove it, but
No, it will have
it's probably okay.
like that.
But okay.
There will be some triangle inequality and inversion.
Probably, yeah. Okay. And then what we have is, okay, so once you put it in the lemma, then one gets that the probability that you sample phi 1 from mu n, okay, is alpha square minus 1 by 2 to the lambda, that it goes, you know, so we calculated the expectations, 1 by 2 to the lambda, probability that it deviates from this value for this epsilon is going to be at most 3 times e to the, okay, I haven't checked this, so I left it as a to do, so we can check it later that all the constants work out. Okay, but then the point is that, you know, so one can therefore write that expectation of phi 1 sampled from mu n of alpha, okay, because yeah, so this is the extra component we'll have, so that's we will figure it out. So this expectation is going to be at most 3 to the exponential minus delta lambda square by 4 times 1 plus 1 times lambda by 1 2 to the lambda by 4. Okay. So what is going on here? So this first term is saying what? So that is the probability with which you would exceed the bound. Okay. So with that, so in that case, you just assume that the value was 1, like the highest possible. Okay. And in the other case, you would have some 1 minus this probability, which is negligible. So you're saying, you know, it's at most 1. So suppose that happens with probability 1, and the value would be, you know, since we want the bound on mod alpha, this gives you a bound on mod alpha square. So when you do the math, which allows to leave as a small exercise, you will get that, you know, just have to move things around and take the average, that the max value that mod alpha takes is this. Okay. So that's the statement. Okay. And this is negligible, right? So this is, which is negligible. Okay, so this calculation is just this, right? That you have mod alpha square is, so you want it to be at most something, so you go lambda by 2 to the lambda 2 plus 1 by 2 to the lambda, and then you can take square roots, and then you can use the fact that, you know, a plus b root would be at most. So you plug that in and you do the calculation, you get that. Okay. Okay, so we have this. So we know that the expectation of mod alpha is negligible using all the machinery we've constructed so far. And now we'll do the last little step and then we're done. Okay, and the second note is that the expectation over phi 0 and phi 1 of trace distance row 0b, row 1b. Okay, so let's compute this. It's going to be what? It's going to be the expectation of phi 0, phi 1. Okay, norm of trace over C of phi 0, phi 0 minus phi 1, phi 1, right? Okay, this is just by the definition. So recall that row sub B was capital B. It was just trace C of phi B, right? That's just by definition. Okay. And now what we do is, so now we expand phi 1 as A times phi 0 plus root 1 minus modulus square phi 0 perp, right? Using essentially this expansion, and then we just substitute. Okay, so when you substitute, and when you substitute, you're going to get phi 0 perp, phi 0, phi 1 0, and you have an expectation over A, right? Because A depends on phi 1, so we're just rewriting the variables. And this is the same as half trace C. So this is something you can check, okay? Write it down. There's just algebra now at this point. Phi 0 perp minus square root 1 minus mod A square A phi 0 perp plus A star phi 0 perp phi 0. Just the Hermitian conjugate, right? Okay. Okay, so all I did was I substituted this expression phi 1 into this, and this is what we get. Okay, and now what one can do is one can apply the triangle inequality and neglect negligible terms to get the following. So you'll have phi 0 perp, phi 0 perp is 0, half of trace C phi 0 minus phi 0 perp, the one norm, okay, plus expectation over A, right? Because the first term, we know that A is negligible anyway, right? So we can just substitute this by 1. So we don't have any expectation over A. The second term still has an expectation over A, but this is going to be at most A, right? Right? Because there's a half and there's a star, so you can take the mod, you'll get this. And this we know is negligible as well. Okay. And now we'll just change the variables. So what we were calling, so these are. So yeah, so now one can relabel them. So we'll just get expectation phi 0 phi 1, where phi 0 phi 1 are orthogonal, half trace C phi 0 minus phi 1 phi 1. Okay, so that's just a change of basis plus something negligible.
In the second term, there was factor square root 1 minus mod A square as well, right? That you wrote.
Yeah, that you can just assume is 1 because you're giving an upper bound. It will be 1 minus negligible, so you just take it to be 1. Okay. So you get this object, and Okay, and then I guess we started with, what did we start with? Oh yeah, right, good. So we started with this object, right? So we started with the expectation of, yeah, so this you can now write as, so this part can be written as, it's just trace distance over rho 0, rho 1, right? Rho 0, 1. Except that now you have the orthogonality condition, and this is without the orthogonality condition. And the only difference is this negligible term, right, which was star that we wanted to show. Okay, so that shows you that deterministic schemes cannot work. Okay, good. So that at least completes that part. Now we're going to go to the construction of a scheme that actually works.
The second term, shouldn't there be a negative sign?
Where?
It's like minus 2 with 1 minus 4.
Yeah, you don't know the signs away, right? So
There is a triangle inequality, so that minus will become plus.
yeah.
So trace num of a minus b is less than equal to trace num a plus trace num b.
Yeah. Yeah, and the intuition is, of course, like these a's could be negative, so you don't know the sign in advance. If it was positive, then maybe you could argue.
So as soon as you use triangle inequality, you cannot argue anything. That will be plus with whatever there. Oh, you are saying that mod a could be negative. That is also not negative.
No, I was saying a could be negative.
That doesn't matter because you are taking norm of that thing.
No, I'm saying if you knew something more about the quantities, then you could give a better bound. When you don't, you have to just put a plus when you're giving an upper bound. Like if you know that a is positive.
If you use triangle inequality, you are done.
I'm not saying anything very deep. Okay. Right. So we completed the impossibility proof. So that's good.
So how difficult is this part that coming from mod alpha square to mod alpha?
It's here, no? So you just
So there is probability also settling out.
yeah. So this expression says what? It says the probability that the random variable has a value greater than this is at most something. Okay. So we take two cases. So in one case, we are saying that the value was, so this bound is satisfied or this bound is not satisfied. Those are the only two possibilities. So we write down the probabilities for each of them. Okay. So I put 1 because it's an upper bound, but you can put 1 minus negligible. And then I'm saying in the case that the bound is satisfied, what is the highest value this thing can take? And then I just solve for alpha, mod alpha, assuming this bound is satisfied.
It's like if the bound is satisfied, the maximum value mod alpha can take is 1. And if the bound is not satisfied,
So if bound is satisfied, why is the maximum value not?
because mod alpha square is not satisfied.
Mod alpha is the component, right? It's the component of a vector, so it can be at most 1.
Of any argument is less than equal to 1.
Yeah. So instead of computing it explicitly, I'm just saying that if the bound is not satisfied, so if it's farther away from the average, what is the highest value it can take? 1, irrespective of any argument. And with probability 1 minus negligible, which I can upper bound by 1, the bound will be satisfied. And if the bound is satisfied, the highest value lambda can take is by saturating the bound. Right. So I just saturate the bound for, if this is for mod alpha square, I can saturate it for mod alpha, or at least get an upper bound even if I don't saturate. So that's all I did. I didn't do anything very deep. Okay, good. Alrighty. So now we're going to go back to talking a lot. Looking at we have not spoken about coset states, right? Not yet. Okay. Good. So now we're going to go back to trying to understand how the construction, how to construct such a scheme. So we looked at an impossibility result, now we look at a construction. Okay. So now if you're following the paper, we are going back to the tech overview. So this is section 1.4 again. Tech overview. And we're going to start from somewhere in between, which is instantiating BL20 using coset states. Okay. So the idea of BL20, let's quickly recall it. Or maybe this guy does recall it. Okay, wait. Let me give you a quick reminder. Sorry, give me a second. I think I got a little bit lost with. Shoot, sorry, I was looking at the wrong set of notes. Okay, so let's quickly recall the scheme by Broadbent. Okay, so let's do a quick recall. So the idea was to okay, so we looked at two schemes. So the first one we looked at was compose one-time pad with Wiesner states, or BB84 states, whichever one you want to call. Okay, so Gen was that you basically return a random theta. Okay. Encrypt using theta of m was doing the following. So it would sample an x uniformly at random. Okay, and it would return m XORed with x, and and it encodes x using the conjugate encoding. Right, this is what we had done. And the intuition was that if you do not know x, right? Sorry, if you do not know theta, then you cannot send this state to two parties, okay? Such that when they get theta later, they can recover the state, right? And then we saw that this scheme manifestly doesn't satisfy the unclonable indistinguishability property. It satisfied the weaker property, right? That it can potentially hide a little bit of information, but not for all messages. And the attack was simple. And then this was modified, and the way they modified it was that they added, so instead of sending h theta acting on x with m plus x, they also added a random oracle. So they added, so you would also sample an alpha. Okay, so they added, maybe let me use a different color. So here the key would include an alpha, which you would also sample. It wasn't immediate why we needed alpha, but it's probably also added, let's just say n. Okay, and then here they added alpha, and the encryption was m XORed with. So now this H is the random oracle. Okay, so this is the random oracle acting on alpha and x both. Okay, so instead of that, and this the other part is the same. So this H theta x. Okay, so this is what the scheme was that they were using, and they could not prove security properly for this. So there were some assumptions they had to make. So they had to either assume, so they basically had to either assume that the B and C adversaries are unentangled, or they had to assume that the message is of constant length, something like this. So this did not quite work. And so now we're going to look at a construction which is inspired by this, but instead of using the BB84 states, now we're going to instantiate the same idea by using what are called coset states. Okay. So the story now is so use coset states. Instead of Wiesner. Okay. And these coset states were first studied by Coladangelo. Coladangelo. Sui, and Zandri. And they were studying copy protection schemes, basically. We may or may not have time to do copy protection, we'll see, but that's where they first appeared. And so we're going to now quickly recall what coset states are, or introduce, in fact, because we don't know what these are. So let's do that. So my hope is that I'm going to be able to give you like a very high level idea of how the construction works based on what it says in the tech overview, and maybe introduce some formal definitions and give like a little bit of the actual proof, and then hopefully we'll complete the actual proof in the coming lectures. Okay, so here's a quick review of coset states. Okay, so they're specified by 3 parameters. Okay, so the first thing is a subspace. So a subspace A of F2 lambda of dimension lambda by 2. Okay. B, you have 2 vectors, S prime, F2 lambda. So these are the 3 parameters. So A, S, and S prime. Okay. And the state is specified. So the states are specified using cosets. So coset A plus S, okay, and A perp plus S. Okay, where A perp denotes the dual or orthogonal, the dual subspace over here. Okay, that's just informal. We'll look at the exact definitions in a bit. So basically you take all elements of the vector space and then you add S to it. So you start with S and add any element of the vector space, you will get a set. So that's the coset A plus S. You take the same vector S and you add any component from the orthogonal vector space.
So are S and S prime supposed to be part of A? Like
S and S prime are not required to be part of A. because otherwise A plus S would just be A, right? There would be no difference.
So they should be excluded from A.
They're just in F2. They may or may not be in A. Yeah, like there's no restriction. Although I think if you make the restriction, it probably won't make, like it might make a negligible difference. I don't know the details actually. I don't know the course. Like there are a lot of theorems about this which I haven't proved. But yeah, we'll assume them for now and then see how the actual construction works and come back to them if you are still interested and have time.
Is not orthogonal to A in some sense. That
I think it's orthogonal as well, but I guess it depends on the definition of duality. We'll come to the actual definition later. So yeah, this is just an informal sort of thing to start with. I think it is actually orthogonal. Yeah, I was writing it today. I can tell you. Yeah, maybe I'll come to it later. Let me come to it later, okay? Because then I'll get distracted. Let's do it later. Okay, so we have this, and now what we are saying is, so you write the, okay, so the states are basically specified using these cosets, and you write them as A S S prime. Okay. Oh, it doesn't actually define them properly. Okay. So I guess we look at the definitions later. Now, okay, the states are specified using this. The state is written as okay. So we look at what the precise definition is later. Let's look at the properties that it satisfies. Okay, so here's the first one, properties. So the first property is that given A SS prime and a classical description of A, okay, there exists an efficient algorithm, efficient quantum algorithm that can output or that outputs both S and S prime. Okay, so we look at a proof of this in just a second. And the second is that no adversary wins the following monogamy entanglement game for coset states, which we'll describe in just a second, with probability greater than cos lambda pi by 8. Okay. Okay, so this is also from CLL Z21. And what is the game? The game is the following. So you have a challenger. Okay, so the challenger samples, samples a subspace of F2 lambda uniformly of dimension lambda by 2. Yeah, okay. So samples A of dimension lambda by 2 uniformly. Okay, and it samples SS prime uniformly from F2 lambda. So there's no restriction that it has to be inside A or not. So it's just a uniform sampling, right? Okay. So you do that, and then you send register A. Okay. Oh, sorry. And then you prepare the coset state A SS prime. A. Oh, sorry. There's a throughout the paper they use the notation A for both the subsystem and the subspace. So it should be clear from the context, but just be mindful, okay? And okay, so as usual, this is sent to an adversary A, and then the adversary sends a bipartite state to bipartite state on BC to Bob and Charlie, and they get a description of the subspace. Okay. So they get a classical description of the subspace. Okay, and they have to output. So they output SB, SB prime, and SC, SC prime. Okay, and you win when SB equals SC equals S, and SB prime equals SC prime equals S prime. Okay, so basically they have to guess these two vectors S and S prime. It's in the definition of ASS prime. I haven't defined it yet. It's something like I think minus 1 to the S dot S prime. Yeah, wait, what is the formal definition? Yes, it clearly tells you I've not proved anything about this myself. Okay, so the definition, let's see. Page 68. 67. Ah, yeah, okay. So it's sorry. So it's A, sum over A, and I mean you don't need the definition actually to understand, but let me just give it to you. It's A plus S. Okay, and then there's whatever normalization. So that's the definition of the. Okay. So yeah, square root size away. Yeah. Somebody was asking something. Oh yeah. So the sum is over all A in the first subspace. Yeah.
Here you're giving a classical description of A. So A could have like exponentially many elements, right? So how will you give it?
Yeah, so I think there's probably some succinct way of giving the description. As I said, I don't, yeah. Probably, yeah, there's probably some way of doing it. Because it's F2 lambda.
Doubly exponential number of subspaces.
Yeah, I'll look into the proofs. Like there's like a lot of background about coset states that I don't fully know, but the properties that we're using is like obviously the fact that A can be efficiently sampled uniformly from F2 to the lambda. So I guess there's something about these vector spaces I don't understand well, and that you can like obviously since the procedure is efficiently sampling it, it has an efficient description, and that's what we're using. But it's a good point. Huh? All of these are very good points, and hopefully.
Sample some finite number of vectors, and then the span of those vectors is
Dimension of
Yeah,
A
but
is lambda.
dimension is lambda.
Dimension of A is lambda.
Yes, it's not exponential. Yeah, it's a poly-sized subspace. Yeah, maybe so that's already answers it. Like even though this thing is exponentially sized, the subspace you're sampling is poly-sized, so it's okay. I'm not fully sure. Yeah, so you just sample a bunch of vectors, I guess,
Yeah,
poly
that's
many.
fine, lambda by 2, but the number of subspaces will be.
That's fine. You just sample random vectors from F2 lambda. I'm guessing that, and take poly many of them, and the span likely gives you a uniformly sampled. There's still something to prove, I guess. It's not.
you have to show that the span still has like polynomially many.
No, you don't need to give like explicit elements of the set, right? You can just give a description that these are the basis for
Yeah,
spanning A, and that's it.
And there will be just lambda by 2.
Yeah. So that's poly. Yeah, thank you. Yeah, thank you for the observation. Good. Anything else? So this part we will see later, or hopefully today, that you can extract S and S prime from the definition. Oi, oi, oi.
And preparation of this state is also trivial, right?
Yeah, once everything is polycized, it shouldn't be hard, right? You can do it. Okay. Shall we move on? Okay, is the definition clear? What's going on, right? So you basically produce this state, and then it has like this similar unclonable property, right? That if you do not know the description of the subspace A, when you have to split it, right? You're arguing that you cannot split it in a way such that both B and C are able to recover SS prime once they learn A. So A is like theta, you know, like theta was here, right? Like you couldn't split it without knowing theta. Even if B and C get theta afterwards, it's not possible for both of them to get X. Similarly here, even if they get A afterwards, it's not possible for both of them to extract S's, S and S prime. Okay. Okay. Oh shoot, yeah. So it says in the story. So let's write it down. Maybe I'll keep that actually. Okay. So story, right? So there's a correspondence with Wiesner states, right? Which was that theta corresponds to A and X corresponds to SS prime, right? Okay, and so one can adapt the construction BL20 to coset states, right? Right. So whatever we did here using theta and X, we can do using A and SS prime, right? So that should be fine. But it's not clear why this helps, right? Okay, so why does it help? Let's see. Okay, so why bother with coset states? What is special about them? Okay, so they differ from Wiesner states in the following ways. Okay, so the first main difference is that given X to the theta, okay, and an oracle P sub X, okay, so what does this do? It outputs 1 only if the input is Y equals X. Okay, so given this, there exists an efficient quantum adversary that learns X without knowing theta. Tell me, it'll be faster.
What is that B and C? Are those registers?
B and C are, yeah, so you prepare, so A prepares like some, like in all monogamy game, prepares some state on registers BC. Okay, and then you send one part to Alice and one part. It's the same as it was. Okay, anything else? Okay, good. Yeah. So B and C are just those. Okay, so The main difference is the following. So it was proved in this paper in 2010. So what was proved? So this is kind of cute, right? So it says that if you're given the Wiesner state, right, we know that if you're not given theta, like it's intuitive that you cannot learn x, right? Because you don't know the basis, so you'll not be able to learn. Certainly not all bits. Maybe you can learn half bits or whatever, but not all bits. And we also know separately, right, that if you're just given an oracle that outputs 1 when the input corresponds to some fixed string, right, then also you need exponentially many queries in the worst case, right, because you can check every single input. So classically, clearly you need exponentially many queries. Quantumly also you can show that you cannot. It's kind of like Grover search, right? Like it's one marked element, you kind of need exponential square root of exponential, but nonetheless exponential, right? But the point is, if you're given both, so if you're given the Wiesner state for encoding some x, and you're given an oracle that says yes when you query at the secret input, okay? If you have a combination of these, then you can actually extract x without knowing theta.
But the queries are very high in number.
No, it's efficient. That's the non-trivial part, of course. If you have exponentially many queries, you don't even need this, right? Then you can just query and learn from piece of x.
Yeah, then you can get x by querying on all these.
Exactly. So here the point is that there's an efficient algorithm that if you give it the BB84 state, like a Wiesner encoding, or conjugate encoding of x, together with the membership oracle, as it's called. Membership meaning like you think of it as a set, or whether it matches a set with a single element. Okay, so this is. I don't think it's a trivial statement. It's a paper. I don't know the proof. Didn't have the time to check, but okay. So this is a property of the Wiesner state or conjugate encoding.
BL20 was the random oracle thing that we discussed.
BL20 was this Broadbent law, like the thing I had written here with with the random oracle and alpha and x.
How can we adapt that using Cosine states?
Oh, because they were using they were still using BB84, right? So what was the?
That is true, but what about alpha? Like,
Oh, you can sample alpha. Alpha was just independently being like, so the only thing was h was at alpha comma x, right?
right.
So instead of alpha comma x, you can do alpha ss prime if you want.
Okay, so x is just SS prime, theta is just sampled from A, and alpha is just sampled independently.
Yeah.
Okay.
Yeah, but that's not the scheme they use. They actually show you don't need to put alpha. It's actually enough to just run the apply the random oracle on SS prime. We'll see how the scheme works, but okay. So far so good. Okay, so what is the next thing? So the next thing is that okay. So this also applies to the monogamy of entanglement games, or game for Wiesner states. I never know whether it's IE or EI. Wiesner states. Okay, so basically what it says is that if A, so this guy, additionally gets access to Px, if A gets access to Px, the monogamy of entanglement game is not secure. Okay, and it essentially follows from one, right? Like if you're given the state and the membership oracle, you can extract x. So if A already knew x, then obviously it can send the description. It can send x to both B and C, right? And then they can extract whatever is needed. Okay. All right, and then the third point is the MOE game for coset states, remain secure even if oracles for S prime are given. Okay, so what is an oracle for S prime? So basically, so you let P A sub S be an oracle. Okay, that outputs 1 if input Y is in A plus S. Okay, and then similarly P A plus S prime, I guess it's with the okay. So this is analogous. Okay, so you let these two things, then no adversary ABC in that game can win MOE for coset states. With non-negligible probability, well, non-negligible advantage, even if all of them A, B, C are all given access, are all given oracle access. So you're given P A plus S and P A perp plus S prime. Okay. Again, this game is what we're going to call MOE for coset states with membership checking oracles. Oh man, time flies. Okay. Is the statement clear?
What we will prove.
Yeah, this is strengthened. Well, actually, I think this was already proved in one of the previous works to some degree. We'll prove something which is, I think, a strengthening of this. Yeah. Okay, so why I was saying this is because this is how coset states are different from.
Also, this is information theoretic result.
Yes. There's no computational assumption. It's just a monogamy of entanglement game. Yeah. Okay. So as I was saying, this is what makes the coset states different from the Wiesner states. Okay, that even if you have access to once you give access to membership oracles, the Wiesner scheme completely breaks down. The coset states continue to satisfy the MOE.
How to argue that no other oracle will help, because this seems like the oracle that you want, but how do I convince myself that this is the best oracle to protect against harm?
Yeah, I guess it will come up in the proof at some point. I don't have good intuition yet. I haven't read the actual proof yet, but maybe they actually say something in the tech overview. We'll see. They did say something about reprogramming games and so on, which was a bit involved. We'll see. maybe I'm saying something wrong because yeah, I think the number of queries, I guess you have to restrict to polynomial, otherwise you could just make exponentially many queries and learn the thing. But other than that, I think it's information theoretic. Yeah.
Okay, the number of queries is polynomial.
I think query bounded. Yeah.
But the adversaries are like.
Yeah. Yeah, because the moment you add oracles, yeah, you have to have query bounds on the oracle calls. Thank you. Yeah, I didn't. I should have been more careful with my statement. But yeah, monogamy of entanglement games are usually just information theoretic. But it's because we added the oracle that we have to be a little more careful. Yeah. So it's similar to when they say unconditional security in the random oracle model. They mean similarly that it's the queries are polynomial, but otherwise it's secure. Okay, good. So now let's look at the construction at least. So
That makes less sense, right? If I have a big machine, then writing circuit for it, I will automatically have many queries.
no, it's just capturing the fact that there's only one problem that you're assuming is hard, but every other problem you're assuming is easy. That's what it's formally capturing. So you're thinking that, at the end of it, we are basically thinking of efficient machines, but we don't know what problems can be efficiently solved and cannot be efficiently solved. So we're thinking that at least, these problems are difficult to solve, so you only give many queries. But like, for example, you're free to solve LWE or invert any one-way function or whatever, that doesn't matter. So that's what is being captured. Okay, so here's the scheme that does satisfy unclonable indistinguishability. Okay. And what is the scheme? So this is essentially the same scheme that we had in BL20 with coset states instead. Right? So what is the scheme? So this, I think somebody had already guessed. So gen 1 to the lambda basically returns a random subspace of size lambda by 2 of subspace A of f2 to the lambda. Okay. So encryption H A comma M samples S prime in f2 lambda. Why have I written lambda A? What is A? So there's no A, I think I just messed up. Okay. And outputs ASS prime. Okay. So the unclonable state, right, together with the message, XORed with the random oracle, but now there's no alpha. Okay. Somebody was asking about alpha, right? Yeah. There's no alpha now. That's the scheme. And decryption is
The message is like n or it's like one bit?
single bit. Okay. So you recover SS prime from the coset state. Okay, so this we argued in we basically stated that you can recover given ASS prime, S and S prime using a quantum algorithm if you have the description of A. Okay, and A intuitively is a very small subspace, right? Like we pointed out, it's a poly-size subspace in an exponentially big space. Okay, and then you output C XORed with the random oracle acting on SS prime, right? So you will recover your state. Okay. So here are some remarks. So the first one is, so they got rid of alpha, which I already mentioned in BL20. The second is in the construction. One does not need membership checking oracles. They're only used for the security analysis. Okay. So in particular, what it means is that, okay, so first of all, it's clear, right? Like in the construction, I didn't say that you needed to give membership oracle access to any party, right? I didn't make any mention of that. But when we do the proof, we will need to assume that you have a way to access the membership oracles. Okay, and it only makes the proof stronger because you're giving the adversaries more power. Okay, so if you can show that the scheme is secure against adversaries with additional power, it's obviously secure against adversaries without that additional power. But funnily enough, you do need to have access to the membership oracles to actually make the proof work, and it's for this reason that the proof for the original scheme, BL20, doesn't go through. Okay, so it's actually not known whether the original scheme can be shown to be secure using Wiesner, Wiesner state. So it's open. At least when this paper was written, I haven't followed up, so maybe you can check. But at least at the time, it wasn't known. It probably isn't known still whether this can be proved secure using Wiesner states. Okay, good.
What does this mean? I mean, this question.
Oh, so it's still not known whether, so BL20 give a partial, like they prove partial security, so they showed security against B and C that are not entangled.
Oh,
It's still not known whether you can show security against B and C that are entangled. So these guys, they couldn't prove the, they show a construction that satisfies this unclonable indistinguishability, but using a different construction. And they're saying that it's not clear that the original construction is provably insecure. So we don't know yet whether the original scheme could work. So that's an open question. Like if one of you is interested, you can think about it. Although I guess it would be quite hard, but everything is hard until you solve it. Okay, so that's good. Okay, so that sort of finishes the thing for what the coset state is and what the construction is. Now we'll say a little bit about the proof, but this is going to be very high level ideas. So basing security on reprogramming games. Okay.
what is this? I mean, will you prove this security of this scheme?
I'll give a high level idea of how the security works.
And this is the headline of.
Yeah. So that's the, not basic, sorry, basing, what am I writing? So it's going to give some intuition on about how the proof works, and then we'll look at the proof in the coming lectures. Okay. Okay, so what property do we need? We require coset states to satisfy. Okay, so this is a simplification. Focus on the n equals 1 case. And I guess they're using interchangeably as the security parameter, is it? Or is it the length of the message? I forget. I suspect it's the length of the message because they're still using lambda. Okay, so we consider the following game. So here's the game. So H is a random oracle from f to lambda across f to lambda to 0, 1. Bound. Okay. So I'll give the game and then I guess we'll have to pause because we only have like about 3 minutes. Okay. So be a random oracle. Okay. Suppose A, B, C have access to so this is oracle access, right? So they have oracle access to the membership oracles. Okay. We define HSS prime perp as being the same as H, okay, except HSS prime is replaced with okay. This is just notation. It's saying that SS prime goes to perp, which just means that this is a new oracle which is derived from the original random oracle, and the only difference is that at input SS prime, this new oracle is going to output perp, okay, instead of whatever value the original oracle was at. Okay. Okay. H0 is defined to be H. Okay, so this is the original. So this is the original random oracle. Okay, and H1 is defined to be the following. So it's H at all points other than SS prime. Okay, and it is 1 XORed with HSS prime at SS prime. Okay. So H0 is the same as the random oracle. H1 just XORs 1 at SS prime. Okay. I think let's stop here. Yeah, let's stop here because I guess we have a class on Saturday, so it won't be too hard to remember the thing.
So do you guys know the time of the class?
No, I'll message you. Don't worry.
Around 3:30.
When is it? Is it on Saturday or
Saturday, like
afternoon? Okay.
Yeah.
around 3:30, I think.
Okay.
Then we decided to meet at 3:45.
3:40.
Yeah.
No.